me, yeah, he moved closer to type theory, really. However, having said this, one should notice that type theory has become more topological. So maybe we are sort of meeting somewhere in the middle. And I have to say, I mean, Martin has done some very impressive stuff using ACTA. I mean, he has created, I mean, there are lots of contributions. This ACTA library, and he's very quick in sort of formalizing things. I'm absolutely impressed. I'm not as good. And I have to remark, even though we are close, there's still, we have got a different taste, you know. So
I just asked Google how long you've known the company. It says approximately since 1995.
okay, so thank you. You asked Google or you asked ChatGPT? Oh, you asked ChatGPT, that's much better. Gemini, yeah? Yeah. Yeah, that's what I mean. I did try already, actually, but anyway. Oh, we, okay, yeah. Thank you. Yeah, we are close, but Martin prefers the sort of Spartan approach to type theory, and I would describe mine as Epicurean. Yeah. So there are some differences, and so now coming here, I thought I talk about something I've been I've been pregnant with for a while, and I thought by promising giving a talk would force me to really make some progress. Yeah, that didn't work. Yeah. So I will. This question mark has to be taken very serious. Yeah, I'm happy. I mean, any input, and I should remark that given my co-author, any hallucinations in this talk are entirely my own. Yeah. Okay. So what do I want to do? I want to really explore higher co-inductive types. So there are this dual to what we know higher inductive types. And actually, we have used them. I mean, Mike has used them in higher observational type theory, which is implemented in NARIA, in a system called NARIA, an experimental system, to define what the vibrant universe. So there's a higher co-inductive definition, which is very, very useful in this context. But I've been looking now for more sort of mundane use of higher co-inductive types, and I thought the signed reals would be a good example. I mean, I've been thinking about this for a while, and I've mentioned it to Martin, and I think he wasn't very impressed. So I'll try again. But the general goal is maybe to understand and to come up with some framework for higher co-inductive types, and then having a nice example is always useful. Relation to Martin, he has done some real stuff a while ago. One thing I would like to understand. So this paper is one where you used signed digit representation. No, am I wrong? Yeah, for the interval domain, but you used signed. I looked at the paper, so don't contradict me. It's not my course.
First hallucination.
Yeah. I know. I looked at the paper. I mean, you used signed in 1996.
And the second one they did this.
Yeah, but there as well, no? Okay. Anyway, so I think this is one of the. I mean, signed digit representation has been used before, but I think it's one of the first times that has been used for doing semantics and not just have more efficient implementations. More recently, I think Martin and Alex, they have looked at different ways with this what I call midpoint algebras, which is better in many ways. And Auke has related them with the hot reals. So, I mean, there are lots of more papers which I don't mention, but I'm going to use this signed reals. But actually, what I'm doing, I think, could also be done in this context, or could be also done for these midpoint algebras. Okay, so what's this talk about? So in homotopy type theory, there's a very nice example of a higher inductive type where we define the reals basically as a Cauchy completion of the rationals. And here it's very essential that we define at the same time the elements and the equality mutually. And it's a nice consequence. We are able to avoid using countable choice to prove the Cauchy completion of the reals because it's already built in. So that's one of the nice uses of higher inductive types, or which I call quotient inductive types, because they're truncated, they're not really very high. And we have been used the same idea to define, actually related to domain theory, Nikolai and myself, and we have defined the partiality monad also in this way, which is basically the free DCPO over a type. And again, you really need quotient inductive types to avoid using axiom of choice. Now, today I want to look at something co-inductive. I mean, we've seen the reals are inductive, but in a way you could say they have more co-inductive flavor. So what I want to do is define this interval, which goes from -1 to +1 this time. And so the constructor is infinite sequences of digits, where the digits are -1, 0, +1. And the semantics, the idea, what I want to approximate are the real numbers in this domain, in this interval. Okay, no surprises here. And what we have here, the idea here is to have really a dual flavor to these quotient inductive types, where we say, I mean, we obviously have a category of algebras, and here algebras and co-algebras in a way are really the same thing, because I mean, the difference between algebra and co-algebras exists when you think about functor algebras, but here you think about a more general idea of algebras, maybe in the sense of generalized algebraic theories, and they're really the same thing. We have a category of algebras, and the inductive type is the initial object, and the co-inductive type is the terminal object. Now, obviously, the question here is, under what conditions do we have initial and terminal algebras? And these conditions are somehow dual, but they don't need to be reduced to functor algebras. I mean, basically, once you have these mutual dependencies, you cannot use functor algebras. So it's actually quite good to think about it more in this general sense and say, okay, we need some conditions under which we have terminal or initial algebras. Okay, so now the first idea would be to work with this algebra, which is a functor algebra, namely to start with streams of digits. So basically you have two functions, head and tail, and you look at the terminal algebra of this thing. But that's clearly not what you want, because for signed reals you have some equalities, and you cannot observe the head of a real. That would give you too much information about the representation. That's clearly not going to work. So yeah, there is some redundancy in the representation, so we cannot have this full stream extensionality. So let's use cons instead. So we have a cons operation given a stream, and we can put a digit in front. and that's the only constructor. Now, that is on its own is not very useful because it will just collapse the terminal. There is a terminal algebra, but it's trivial. It's 1 point. So I mean, instead, in the initial case, you want to add something, but here I want to identify things with equations, but here we want to do the opposite. We want to make difference. We want to be able to differentiate because everything is already identified. So it's sort of like a natural duality. So we need to add some, not equations. They're really co-equations. They're really observations. So let's do something else. Let's say, okay, we say everything is generated, and here I use the truncated existence. So for every element of the interval, there exists a representation as a const, but I'm blocking the access to this. On the other hand, I want to say that const is injective. But this is already too much. These are too many observations, because actually you can see that from this you can define head and tail, and you get back the observations you want to avoid. So we went a bit too far, too many observations. So we have to be a little bit careful in what we do. So here is some more modest observations. So first of all, let's look at the injectivity. Here I'm doing only argument-wise injectivity. So if the tail is the same, or here if the head is the same, I get some kind of injectivity. I get argument-wise injectivity. I don't know what the right word for this is. And then I have some no confusion. Certainly, if I start with -1 or +1, there's no way they can meet. So here I get this is a co-equation. This is impossible. That's fine. This is like a destructor of the equality. Yeah?
Where you need x to be all ones and you put y to be all -1s, then you will get 0.
Oh shit. Yeah.
But anyhow, this is not what you want, so it's doubly wrong.
Okay. So yeah. So I should fix this. You're saying, yeah. So because if I get x I get up to 0. Yeah, I think I saw this once and then I forgot about it. Okay.
That implies that both are wrong. That
Pardon?
implies that both if I said it's wrong, then it's wrong.
Yeah. No, I just need to know how to.
It's wrong. It's okay.
It's okay. Okay. So yeah. Shit. Okay. So I want to avoid this head confusion. So I can cancel if the heads match like here. But so where are we now? We have some observations. Certain things are put apart, but still too many things are identified. So anything which has a 0 instead of a 1 is still identified. So we need some cross-head equalities. No, we need some of them, but not all of them. I mean, clearly, sometimes a stream starting with 0 and a stream starting with 1 gets identified, but not always. I mean, in the moment, all streams which then differ 0 and 1 are getting identified. So let me remind you of the semantics. So I'll discuss the definition of these Scott brackets in a second, but let's just for clarification. I mean, what's the meaning of d cons x is d divided the digit divided by 2 plus the rest divided by 2. So it's 1 to the 2 to the n representation, but we can write it down this nicely recursively. And what we want is obviously we want to have soundness of all the observations, but we also want completeness, so we want to actually capture exactly the interval. Okay. So there are some useful operations which are the sort of recursive increment and the recursive decrement, which the easiest to best to understand this is we add a half. We add a half to whatever we have, and here we subtract a half and divide the input by 2. So it's like if you're in binary, if you have successor on binary and predecessor on binary, and you do this just co-inductively, that's what you get. Yeah.
Excuse me.
Yeah.
I have a question. So with this definition, can you go back 2 slides? I think there's a problem with that. I don't think that no confusion axiom is true, because if x is like ones repeating and y is negative ones repeating, then they're both 0.
Sorry, what?
You-
Same as Andre already said. Okay.
Oh, you already said that.
Yeah. Okay. So I have to. Yeah. So that's the point. So we met at 0. So I have to be more careful here, right? So yeah. Okay. I didn't check this first equation. I did check the other ones. Okay. Thank you. What's no? Okay. So we can co-inductively define inc and dec. Yeah, as I say, it's just the usual the usual definition of, as I say, increasing. I mean, the successor and the predecessor of sequences, binary sequences, but here done co-inductively. So what I really want, I mean, I want to maintain these equations, which you would add if you do this inductively, but we do it co-inductively, so we add sort of in a way, the inverse, these observations, which basically don't destroy this identification. So we say if we start with 0 and this is the same as the increment of y, then we also know that we can put -1 in front and 0 in front of y, and it's easy to check in the semantics. This one I did check that this holds, and the same is the symmetric case, the observation for decrement, and just everything turned around. And so we can still, so I mean, we had no trouble before to get these equations, but the point is that these equations survive, but other unwanted equations get destroyed by these Horn formulas. So that's maybe the general flavor here, that we add these observations, these co-equations, to enforce some equations which we actually want, but identify everything else. Yeah, well, no, keep everything else apart. So now I already used this these Scott brackets, but actually this is not really a definition, because cons is co-inductive, and so this is not, we cannot define things by recursion on the streams. Instead, we can do the following. We can define a map in the other direction. That's okay. So we can define a map from the semantics into the syntax, which we call quote. And this is given by this equation, which is really what's called a co-pattern match. And from this, we can then extract the semantics by saying, okay, for every x, we have a y, which we have an inverse to y, which is the semantics, but this is in proposition, so we are allowed to use this gen principle, and then we can extract from this proposition the actual semantics is the first part of the pair, which is which just satisfies. No, I don't know why there are two d halves. That's a typo. I mean, this is just what I had before. Yeah. Sorry?
You've got counting steps.
Yeah.
You've got so which is syntax?
So I mean, my co-inductive definition is the syntax, and the semantics is my meta-theoretic reals. I mean, the interval my meta-theoretic reals. And I want to have a function evaluation which goes from my co-inductive definition, my terminal coalgebra. So I is the terminal coalgebra of the structure. After I fix this problem with a zero, bloody hell, zero. Who cares about zero? And so what we want to, I mean, this intuitive idea. We want to define this function which, given some syntax, some cons, gives me a real number, right?
So if it just stays
Yes, so I want to do it with co-inductive definition with these co-equations, yeah. Right. I mean, there are other better ways to do this, yeah. So I'll want to do it this way, yeah. Okay, so the semantics now we can extract by the projection and simplify. I mean, yeah. Okay, so then saying what's not. Okay, so then I want to prove completeness, and okay, so I think it's not too hard, but I haven't really had time to think about this. And the other thing we could add is the other direction of my Horn formulas. I put them if and only if. This is sort of like adding eta equations, but I don't think that's necessary to get completeness. I think it's useful to get some relative completeness, conditional completeness. Okay, so there's lots of things to be done. I mean, first of all, fix this problem. I hope you've got an idea how to fix this, yeah? Okay, that's good. Thank you. Yes, so then it should be sound, hopefully, and then proving this completeness conjecture, and maybe even some conditional completeness, whatever it means, and also compare it with hot and quit reals. And I think maybe I could also use these midpoint algebras, which are more modern way to do this stuff. And in general, I would like to develop a general framework for higher co-inductive types. And in particular, identify the conditions under which terminal algebras exist, and use them for modular presentation of these observations. Okay, that's all.
Okay, so maybe Andre, if you really shout, I know you can do it. Yes.
Also, we want my microphone. Okay, sorry.
Well, I think Andre might be the one person that people online can actually hear, but we have time for one very quick question. So this is going to. Yes. Let's do it anyway. Okay.
So from what I understand, now I don't have to shout, right? Okay. So from what I understand, this is about getting a good combinatorial description of how these equalities are going to work. And one thing you might want to look at is getting rid of 0 and have just digits 1 and -1 and use the golden ratio as your base. because then what happens is that the sequence 1 minus 1 minus 1 is equal to 0, is equal to minus 1, 1, 1. And I think these are the only finitary combinations of equations that you need to consider to properly describe the quotient. This is 1990s stuff when Martin and I also and other people were doing this kind of thing. So there are papers, I don't know who did golden ratio, somebody did golden ratio, and Pietro did Gian Antonio, yes, thank you. So that one might be easier to handle combinatorially. That would be my suggestion to look at. And it would be super cool if you had golden ratio. I mean, you have to also admit that.
Just one.
I have another question. Can you
Yeah,
hear
go
me? Yeah, near the end, you said something about relative completeness. What does that mean? How's that different from completeness?
Yeah, it means, okay, if I only have a thing about the reals, the closed reals, then I should have completeness. But if I make some assumptions and derive an equation, then I need the equations in the other direction to have any hope of it being complete.
So you mean like in a different context where like we have an assumption of equations, then the equations you can deduce, they may not be the same.
Yes.
Okay.
Given the time, you have to move on.
Okay.
Towards the end.